Let me begin with a question. How do we draw a line that separates ideas? Not metaphorically, but mathematically. When we look at data, and I'm talking about real data, it rarely comes neatly divided. It is very messy, it overlaps, it lives in a high dimensional spaces where we cannot even visualize it. And yet, there exists an algorithm, a machine learning algorithm, whose entire purpose is to draw the best possible boundary between the categories. Not just any boundary, the optimal one. Today, we're going to talk about support vector machine, one of the most elegant and geometrically beautiful ideas in machine learning. And what makes it powerful is not complexity, it's actually its precision. So let's begin our presentation on the next slide. So let's continue with the presentation. A support vector machine, or for short SVM, is a supervised learning method. That means we already know the labels. We're not guessing structure blindly. We're learning from examples. Now, here's the core idea. If I give you two classes of point, let's say red and blue, you could draw many lines separating them, infinitely many. But the support vector machine doesn't want any separating line. It wants the one that maximizes the margin. The margin is the distance between the boundary and the closest point from each class. And those closest points, they're called support vectors. Here's the genius behind this machine learning algorithm. The entire model depends only on those few critical points. Not all the data, just the most informative data. So support vector machine says, I will choose the boundary that stays as far away as possible from the nearest points of both classes. Why? Because the larger margin means better generalization. It means more confidence. Now, what if the data is not linearly separable? That's where kernels enter into the picture. And kernels are magic, but mathematical magic. They allow us to project data into higher dimensions without ever explicitly computing those dimensions. So support vector machine can handle linear patterns and non-linear patterns. It can do classification, regression, even outlier detection, all from one geometric idea, okay? So let's continue on the next slide. Okay, so at this point, I would like us to zoom out, okay? And machine learning splits broadly into supervised and unsupervised learning, as we covered that in previous lesson. And support vector machine lives firmly in supervised learning under classification. It actually competes with naive Bayes, discriminant analysis, nearest neighbors, neural network. Under regression, we have support vector regression. Now, what's interesting is this, okay? Here's what very interesting about this machine learning algorithm. Support vector machine is not probabilistic like naive Bayes. It's not tree-based like decision trees. It's not gradient descent like neural network. It's geometric optimization. It solves a constraint optimization problem, maximizes margin, subject to classification constraint. Okay, and the mathematical framing makes it incredibly powerful in high dimensional spaces. And that's why support vector machine historically dominated fields like text classification, where you might have tens of thousands of features. When features explode, that's where support vector machine shines. And now let's talk about assumptions. Okay, these are the requirements to use a support vector machine. First, support vector machine is a non-parametric machine learning algorithm. That means it does not assume your data follows a normal distribution. It does not assume equivariances. It does not assume Gaussian structure. It makes one core requirement. You must have labeled data. And there must exist some separating boundary, whether linear or achieved through a kernel transformation. If the data is completely inseparable, no model will perform miracles, okay? There is no model that can do that for you. But if structure exists, support vector machine will find that boundary that respect the structure while maximizing the margin. And the beautiful part, it does this without caring about the underlying distribution. That flexibility is so powerful, but it also means that you must be carefully when tuning it. Okay, so let's continue on the next slide. So let's be honest. No algorithm is perfect. I don't think there is any machine learning algorithm that is perfect. Okay, support vector machine performs extremely well in high dimensional spaces. When the number of features exceed the number of samples, many models struggle, but support vector machine does not. Second, it's memory efficient because only support vectors define the model, not every point. Okay. Third, versatility. With different kernel function, for example, linear, polynomial, RFB, we can adopt a complex boundaries. Now, what are the trade-offs? Well, support vector requires careful selection of hyperparameters. For instance, the regularization parameter C, the kernel parameters like gamma. If you choose poorly, you may overfit. Second, it can be computationally intensive, especially for very large data set. And third, it does not naturally provide probabilities estimate. It tells you class membership, not probability confidence, unless additional calibration is performed. So, in conclusion, support vector machine is powerful, but it demands respect. And now let's actually talk about application. Let's talk about the real world. Where does support vector machine actually show up? Well, they show up in text classification, span filtering. And why do they show up in this area? Because text data is high dimensional. Every word is a feature. Support vector machine handles that beautifully, okay? Bioinformatics, protein classification, cancer detection. When the data space is complex and dimensionality is high, support vector machine performs reliably. For instance, in image recognition, handwriting recognition. Before deep learning exploded, support vector machine was the state of the art in many computer vision tasks, even in finance, fraud detection, financial forecasting, where decision boundaries are subtle. And here's the key insight. Support vector machine is strongest when the boundary matters more than distribution. When you care about classification precision, okay? Support vector machine becomes extremely attractive, okay? And those are the applications of support vector machine. So let's close this presentation. Let me leave you with this idea. Support vector machine are not flashy. They're not deep learning. They're not massive transformer architecture, but they represent something intellectually pure: optimization, geometry, margin maximization. They teach us that sometimes the most powerful solution is not about complexity. It's about choosing the boundary that gives you the most confidence, the most space, the greatest margin for error. And maybe that lesson is beyond machine learning, because in data and in life, the margin often determines resilience. And, uh, and that's the end of this presentation. I want to thank you for listening to me talk about support vector machine. And I wish you a wonderful day today. Take care. And now let's review the Python code, the support vector machine Python code. And the thing about this code, it is pretty much like the previous codes that we had discussed. They all follow the same pattern, all of them. So it's going to be pretty much the same type of code, the same structure, the same sequence. But let's look at it. Let's look at it anyways. But honestly, it is the same pattern, the same sequence. It is nothing new. Okay. In fact, it might be a little bit simpler than other Python code. But let's look at the code. Okay, so let's look at the first block of code, and this one follows the same structure, the same direction as the previous one that we see before. You import the libraries that you are going to be using to build a support vector machine model. And this is the second block of code. And this one does just like the other ones. This one uploads the data set. Okay. And here, in this case, the data set is health.csv. And then we actually look at the first 5 rows of the data set. And in order to actually inspect your data set. And this block of code, we are just getting some summary statistics, right? In addition to that, we are checking to see if there are any missing values. Remember that if we have any missing values, we need to delete those missing values. Otherwise, the machine learning algorithm is just going to stop. It is not going to work. If there are missing values, your machine learning algorithm is just going to give you an error message. In this block of code, what we do, we are actually selecting the features that we are going to be using. And the features that we are not going to be using, we're dropping them. So we're dropping all of those features that we are not going to be using at all. And we're keeping the features that will be used in the support vector machine model. In this block of code, we convert the diagnosis, which is the dependent variable in this case, the target variable, okay, or the target vector. So diagnosis is we're converting this dependent variable from categorical to numeric variable. As you can see, now we're mapping benign to 0 and malignant to 1. So if the diagnosis is benign, then it's going to be 0. It's going to show up as a 0. And if the diagnosis is malignant, it's going to show up as 1. So we're converting the categorical variable into numeric variable, because remember that machine learning algorithm, they only read numbers. They cannot read letters, okay? They cannot read characters, they can only read numbers. So we must change any characters into numbers. And that's what this block of code does, okay? Now, in this block of code, all that it is happening here, we are literally selecting the features and we are saving them to the variable x. And we are selecting the dependent variable, which is diagnosis, and we're saving it to the variable y. And once we did that, then we actually print the first 5 rows of all the features. So let's look at this block of code. So before we train the model, we need to look at the data, okay? Because that data is going to tell us a story if we let it, okay? If we let it. And here we are plotting 3 features, right? The radius mean, the texture mean, and the area mean. And immediately we notice something, right? Radius and texture, they are fairly smooth, almost bell-shaped, right? But area stretches, it has a long tail. Some tumors are much larger than the rest, and that matters. Not because support vector machine needs normal data. It doesn't, to be honest. It does not need normal data. But support vector machine cares deeply about scale. If one feature has much larger values than others, it can quietly dominate the decision boundary, not because it's more important, but because it's bigger. So this simple visualization tells us something very powerful. Before we train a support vector machine, we must standardize it because margin-based learning and, because in margin-based learning actually balance really matters. Okay, it is important. Okay, so let's look at this block of code. And actually, let's take it a little bit, let's go a little bit deeper. So you know the histogram show distribution, but box plots, they show structure. And here we look at median, spread, and most importantly, outlier. Notice something immediately? Look at the area mean. The area mean is really operating on a completely different scale. Its median is far higher than radius and texture. But more striking, look at those dots about the whiskers. Those represent outliers, especially in area mean. And this matters because support vector machine tries to maximize the margin, but extreme values can influence where the margin lands, not because they're common, but because they are far away. So this visualization confirms 2 things. First, scaling is absolutely necessary, and second, we must be aware of extreme value exists. And in margin-based learning, distance is everything. Okay, so let's continue and let's look at this block of code. And on this block of code, I want us to zoom out a little bit. And this isn't about distribution anymore. This is about relationship. Each square in this heat map represents correlation between 2 features. Dark red means strong correlation, but blue means negative correlation, and white means weaker or non-existent correlation, okay? And immediately something stands out, okay? Look at what actually stands out. Many of these features are highly correlated. Look at radius mean, perimeter mean, and area mean. They move together. And that makes sense because they all measure size. Now, here's the key insight. Support vector machine does not require independence between features. Well, but when many variables are strongly correlated, we are essentially feeding the model repeated information. It's like telling the same story 3 times. And that can increase model complexity without adding new signals. So this visualization tells us this data is rich, but it's also very redundant. And with building strong model, clarity beats duplication. And in this block of code, we are just doing one basic thing. We are splitting the data set, the original data set. We are splitting the original data set into a training set and a testing set, okay? And about 30% is going to be used for testing, and 70% is going to be used for training. And that's what this code does here, this block of code. And this block of code, all that is doing is actually scaling that data set. Okay, that's pretty much it's doing because you gotta scale the data set. You're going to make sure that no one feature has a greater influence than the other features. And in this block of code, all we are doing is actually training the model. We train the model, and that's all this block of code does. And now let's look at this block of code, and actually let's actually look at the output of this block of code. Okay, so now we test the model. So no more theory, no more visualization. Just we focus on performance. Okay, so our support vector machine achieves an accuracy of 95.9%. Okay, on the testing set of the data. Okay. That means it correctly classifies nearly 96 out of every 100 tumors. But accuracy alone isn't enough, especially in medical diagnosis. So we look at the confusion matrix. Out of the 179 cases, the model classified correctly about 107 of them. Okay? So that means zero false alarm there. For malignant cases, 57 were correctly identified, but 7 were missed. That's important because in cancer detection, false negatives matter more than false positive. Now, look at the recall for malignant tumors, 0.89. That means that the model detects 89% of the actual cancer cases, and that is very strong. Not perfect, but strong. And that's the key takeaway from this. The support vector machine performs very well. High precision, high recall, balanced F1 score. But in a real world medical system, even small miss rate must be taken seriously. Machine learning gives a very powerful tool, but evaluation gives it a lot of responsibility. And now let's look at the last output of this Python code. Now, we visualize something very powerful here. No equations, just geometry. On the axis, radius means. On the y-axis, area mean. And the color represents diagnosis, okay? Blue is benign, red is malignant. And immediately you see something here. As radius increases, area increases. And that's natural because bigger radius means bigger area. But more importantly, malignant tumors tend to live in the upper right region. Higher radius, higher area. Benign tumors cluster toward the left, smaller, less extreme. Now, here's the key insight. You can almost imagine a line separating these two groups, not perfectly, but clearly, and that is exactly what support vector machine is doing here. Is finding the boundary that maximizes separation between these two clouds of points. This plot gives a geometry intuition. And you gotta remember that support vector machine is not magic. It is drawing the smallest possible line between the patterns that already exist. And, and this is the end of the code presentation. Have a wonderful day. I hope you learned something today. Take care.